Okay, it's 7 o'clock and we're going to start the additional science physics revision session. So we're going to cover the first half of physics in this revision session. Don't forget from Nodeswood to put any comments that you have on the comments page on Frog, as well as your name, so we know who's watching and we can answer some of your questions as we go along. So let's start first of all with some little basic stuff about equations that's really important. You get in your exam this data sheet. This is just one half of it, and you'll get another side of this data sheet as well. Do not ignore it in your exam. It's really, really important for you to get marks. And it comes with the equation on the left-hand side and what each of the letters mean on the right-hand side. What it doesn't come with, which is really annoying, is it doesn't come with units. So you notice here there are no units to help you out. You need to remember those for this P2 topic. Some general top tips of physics that I'm going to model as we go throughout is to use a highlighter to highlight key parts of the question. And you can take one into your exam, or you might even be given one in your exam by your school. And also you need to know how to use this data sheet to gain points on your exam. Probably about 10 points, 10 marks on your paper will just be to do with being able to use this data sheet. And in relation to data, we need to remember our units. So with that in mind, let's first of all think about the units that we need for this P2 topic. What I'd like you to do is have a look at each of these words and see if you can name the units for them. So first of all, energy. Think about the units for energy. Do you know them? They are joules. A capital J must be a capital. Power is measured in watts, a capital W. Do you know the units for velocity? Think through these in your head as we go through. The units for velocity are meters per second. The units for mass, do you know the units for mass? The standard unit that we use for mass is kilograms, not grams, but kilograms. Over here, we've got work done. Work done is measured in joules, and that's really important. We'll come across that again as we go throughout this tutorial, this work done. Acceleration. Do you know the units for acceleration? Well done. If you remembered, they are meters per second squared. How about force? Well done. If you remember that units for force are newtons, it must be a capital N. Couple more left. We've got height and we've got weight. Height is normally measured in meters, not centimeters, not kilometers, but normally in meters. That's our standard unit. And weight is measured in, hope you got it, newtons, because weight is a type of force. Okay, so these are just some, there's a few others, but these are just some of the units that we need to remember for P2, especially important if you're doing higher, because there's a lot of questions where you might have to convert the units. Okay, so for example, if you found this in kilowatts, you might have to first do a conversion to watts. If you found a unit in megajoules, you might have to do a conversion to joules, for example. Now, we're not going to go through these conversions in big detail today. Hopefully you know them yourselves by now. If not, I'll cover it in another video. But you do need to bear these in mind throughout this tutorial. So first of all, I really want to just highlight some good practice for when you're answering equation questions in the exam. So here we've got an example of some of the equations that you will get on your data sheet in the exam. And just over here, 3 questions. And I really want you to be super happy whenever you see any equations involving numbers and that phrase that says use an equation on your data sheet, because these are easy marks to pick up. All you need to do is highlight the key information you've got, select the correct equation, and put your numbers in. So I'll show you now exactly what I mean. This question here says calculate the force needed to accelerate a 1.5 kilogram ball at 4 meters per second squared. So what I'd like you to do in your exam is highlight the key information and then write next to it what it means. So 1.5 kilograms is a mass. 4 meters per second squared is our acceleration. And we've been asked to work out force. So all you need to do is look over on this data sheet and find an equation that links force, mass, and acceleration. And if you were to look through, you'd look for those words on the right-hand side here. You'd look for the words force, mass, and acceleration, and you would find this equation here. And all you then do is write this down over here. So you've got force equals mass times acceleration, and then you put your numbers in. So F equals 1.5, which is our mass, multiplied by 4, which is our acceleration, and that would give us a force of 6 newtons. I'm going to do exactly the same thing here on this next question, just a random question. Calculate work done when a 50 Newton force is moved 2 meters. So I go to my data sheet, I look for an equation that links work done with a force and a distance. And after looking at these words along here, work done, force, distance, I come across this one here. And I simply copy it over. So the first thing I do, W equals F times D. And I end up with work done equals 50, which is my force, times by 2. So work done equals 100 joules. Finally then, exactly the same thing, but I just want to highlight a couple of things that will come more often in the higher tier. This says calculate the extension of a spring if a 50 newtons force was applied to a spring with a spring constant of 20 Newton meters. So I look over here again for the correct equation to use that links extension, force, and spring constant. And I look for those words along here and I'd find this one. Force equals spring constant times extension. So the first thing I do over here would be to write it down. So I'd have force equals spring constant times extension. But for the higher tier, this is one thing that I want to highlight, you will need to know how to rearrange equations. So we need to make this extension because we've been asked to calculate extension. So if we divide both sides by k, to get rid of the k here, we'd end up with E equals F divided by k. So we put our numbers in now and we get E equals force, which is 50, divided by our extension, divided by our spring constant, which is 20. And we'd end up with an extension of 2.5 meters. So for the higher tier, make sure you can rearrange equations. That's really important. And the second thing that I highlight that you need to look out for is, are they in the correct units? Now, luckily, these ones are. You've got newtons and Newton per meters, but if they're not in the correct units, be prepared to convert them first of all. Now, sometimes these come up in foundation where they're not in correct units, but it's more of a problem if you're taking the higher tier. So here's a couple of questions for you to try. If you're doing foundation, I'd like you to have a go at numbers 1 and 2. And if you're doing higher, just have a go at 2 and 3. So I'll just give you a couple of minutes to highlight the key points and then we'll move on. If you've just joined us, please write your name on the frog page so we know who's tuned in. And I've just said for foundation to have a go at these couple of questions here, and for higher tier to do 2 and 3. Okay, welcome to those people that have just joined us. Just to briefly recap what we've done, we have just talked through the importance of using the equation sheet and the fact that you would have to remember the right units because they don't show your units here. So you have to remember the right units, and for higher tier, you've got to remember they'll trick you out by using things such as megawatts or kilojoules or something like that, and you'll have to do some conversions first of all in some cases. So let's go through the answers to these questions. Again, modelling, good practice of highlighting the key points. It says calculate weight of a 7.4 kilogram cat on Earth where the gravitational field strength is 10 newtons per kilogram. So you should write all over your exam paper, have a look what you've got. It's asked to calculate weight, it's given us a mass, and it's given us a gravitational field strength. So we go over here, select the right equation because we've had a look at these words here. You've then got W equals, so W equals 7.4 for our mass multiplied by 10 to give us 74 newtons. Remember, weight is a force. It's the force with which you're pulled down to Earth. Now then, the work done. Down the bottom here, again, highlighting the key point, the work done when a boy pushes a box with a force of 5 newtons over 3 meters. So we choose our correct equation. We look for the words here, work done, force and distance, and we'd find this one. So W equals F times D, where W equals force 5 times 3 meters. Work done equals 15 joules. Final then one, typical one that you might have to do on higher tier, calculate the acceleration of a 10-gram toy car with a resultant force of 20 newtons pushing it forwards. Hopefully you would have noticed over here that we have a mass in grams, not kilograms. So first of all, really common on the higher tier, we'd have to convert it to kilograms first of all. So we do 10 divided by 1,000 to get our mass, M, as 0.01 kilograms. And we then need to find the correct equation to use. So we've got acceleration, force, and mass. And we look over here, and we'd find this one. And you're very lucky, the top one they've already rearranged for you. So acceleration equals force divided by mass. So acceleration equals 0.01 kilograms, force divided by mass, so 20 newtons divided by 0.01 kilograms, and that will give you an acceleration of 2,000 meters per second squared, which is probably a little unrealistic for a little toy car, but never mind. Okay, so that is just the basics of using these equation sheets to be able to get some really easy marks on your paper. As I said, they could get you up to 10 marks, so it's really worth knowing. I've had a question about if you forget the units, how many marks do you use? That's a brilliant question because I'll show you a little trick. Normally with the questions, if they give you the units already, so if you've got a dotted line with like meters at the end or joules at the end, often the question is 2 marks. What you'll notice is if they don't give you any units and you've got to remember them, the question will be 3 marks. So if you do forget the units, then you'll only drop 1 mark. But I'll give you a little neat trick, a way to work out some of the units as we come across them a little bit later on. For example, hopefully you'll find this is a little bit of a light bulb moment. If force is measured in newtons, extension is measured in meters, and if you can't remember the unit for spring constant, what you can do is help yourself by rearranging the equation. So if spring constant equals force divided by extension, then if we think about the units for these things, we can write it another way, that spring constant is newtons divided by meters, and that is the units for spring constant, newtons divided by meters, newtons per meter. Okay, so that's a nice little neat little trick. If you can't forget the units, it doesn't work for all of them, but it will work for quite a few. Okay, moving on then, is this equation, which you'll see on your equation sheet, A equals V minus U over T. My font is made at capitals, but you'll see it as lowercase in your real exam. And I've purposely chosen this equation because sometimes it tricks people out a little bit. So I'm going to let you have a go at these yourselves, and I'll see if you find out the pitfalls or see if you're happy with them. So I've put up here what A is, acceleration, U is initial velocity, V is final velocity, and T is the time taken. And these are the questions I'd like you to have a go at, and then I'll go through them with you. A cat was running at 2 meters per second and then accelerated to a final speed of 5 meters per second. I'll highlight the things for you so you can see them a bit easier. So 2 meters per second, accelerating to 5 meters per second. It took 2 seconds for the cat to reach its final speed. Calculate the acceleration of the cat. So if you have a go at that one first, and then we'll go through that one, and then we'll jump to number 2. Okay, so hopefully that gave you enough time. I'll start by writing down the equation. It's always good practice to do that. So A equals V minus U over T. And we look for our numbers. We've been asked to calculate acceleration. So we need to work out A equals. Now over here, I want you to be writing on your exam paper that this is the final velocity, V. This is the initial velocity, U. So A equals V minus U divided by T, like we've got over here. So we just put our numbers in. A equals 5 minus 2. And then we divide that by the time it takes, which is 2. So we'll end up with 3 over 2, which will give us an acceleration of 1.5. Remember the units, meters per second squared. Okay. For the second one, I've purposely put a little pitfall in there. See if you can work it out. Let's go through number 2. A parked car started its journey and reached a top speed of 5 meters per second. It took 5 seconds for the car to reach this speed. Calculate the acceleration of the car. Purposely written this one, so have a look at it, see if you can do it, and then we'll go through it in just a sec. Okay, so for this one, this is the common one that you'd see in an exam. This is wanting us to calculate A for acceleration, and they give us a top speed, so our final speed of V, and it took 5 seconds, which is our T, for the car to reach this speed. Now, this is really common that there's not an obvious number for its initial velocity. There's not an obvious number for that U, because what they do is they imply it in the question. They've told you here that the car is parked. So our U is going to be 0 meters per second because it's parked. So let's go through this question. We need to calculate A. A equals V minus U divided by T. So A equals 5, which is our final velocity, minus 0 divided by 5, which gives us an acceleration of 1 meters per second squared. So really well done if you've got that one. Bear in mind that they will do that in the exam, and they'll say, for example, you know, a dog is sitting on the ground or something like that, and they'll imply that that initial velocity is 0. You also might end up with a negative acceleration as well. So if something is slowing down, for example, you might get that negative acceleration to show a deceleration. And don't worry about that at all. You can write an answer, for example, negative 5 meters per second squared, if that is how the answer comes out. Now, what I would say is just have a look at the acceleration. It will just help you relate it to the equation a bit more. Acceleration is, we can talk about it in lay terms, as like speeding up and how quickly you speed up. And if you look at the equation, that makes sense because it's saying how much have we sped up over time? What is our change in velocity? So that is one way that you can calculate the acceleration. So hopefully you're happy with those ones. We're going to move on now, and we're going to look at work done. Again, we're going to look at this in terms of the equation and W equals F times D. And I want you to have a look at these questions because I'm going to highlight something to you which will hopefully be really important when it comes to the exam. Now, the first idea, it says it calculates work done when a box is pulled with a force of 10 newtons for 0.5 meters for 2 marks. Okay, so in this question, we do just like we did before. We'd annotate it. So we've got work done, we've got a force, and we've got a distance. And we'd look in our data sheet, but I've given you the data here. We need to remember that work done is measured in joules, force is measured in newtons, and distance is measured in meters. So we go ahead here and calculate our work done. W equals F times by D. So W equals 10 multiplied by 0.5, and that will give us a work done of 5 joules. Bear in mind that they might give you other random bits of information in the question that you might not need to calculate the work done. So just be careful that you are using a force times distance. Now this bit's super important. You should recognize this, okay? Because after a big calculation, maybe worth 2 or 3 marks, it's really common in the exam for a 1-mark question. And the 1-mark question will say calculate the energy transferred. I want to highlight to you that it is just 1 mark. This should be alarm bells for you to say, I don't have to do that much work for this question because it's only 1 mark. They don't want me to do a massive calculation. They just want me to simply copy down the answer that I've put before, which is 5 joules. So look out for that. That's really important. And the science behind that is because work done equals energy transferred. And if there is one thing that I would encourage you to write down and put on your bedroom wall, it would be this idea. Work done equals energy transferred, because this will come up again and again and again. So here it is again down here in a second example. Have a go at this one yourself, and then we'll just check the answer. Okay, so we have our highlighted examples here. So we've got 20 newtons of force over 15 meters, and we have to calculate work done. So we start off, work done equals force times distance. So work done equals 20 newtons times by 15, which is 300 joules of work done to push that trolley 15 meters. And then again, we've got this 1-mark question which says energy transferred, and that is 300 joules. Okay, so that is work done. I will highlight again how important remembering the fact that work done is energy transferred by putting it on its own slide. Okay, please write this down. Please remember this because I'm pretty sure it will come up somewhere in your exam. The only other thing I want to go through very briefly on work done is because it is energy transferred, so work done is the same thing as energy transferred. When work is done by or against friction, the energy transfer that happens is from kinetic energy into heat energy. Okay, so remembering work done as energy transfers will help you with your understanding of this. So when work is done by or against friction, the energy transfer that happens is kinetic into heat energy. This is the reason why if you have a meteorite coming through the Earth, it will be burning up, okay, as it comes through the atmosphere, because that work is being done by friction and kinetic energy is being transferred into heat energy. Similarly, on a wheel and brakes, you've got the brakes doing work to stop the car, and that kinetic energy will be transferred into heat energy. That's why your brakes heat up. So this is just another thing to bear in mind because it comes up a few times on the exam papers. Okay, moving on then from work done and energy transferred, another really important link to be making is the link between gravitational potential energy and kinetic energy. So you need to have in the back of your mind for these questions the idea, again, that work done is energy transferred, because sometimes they link these questions. Why wouldn't they? Because if you're looking at energy, you can also say that you're looking at work done. So bear that in mind. I'm not going to do any questions on that at this point today, but you need to remember that. So we got two equations for energy on our equation sheet. We've got one which is gravitational potential energy, and that's depicted by this equation. Gravitational potential energy equals mass times gravitational field strength times height. And over here we have kinetic energy, which is EK. We describe that as EK for half times m for mass times velocity squared. So we've got two equations that we can look at, but often, and especially on the higher paper, they will try and link these two ideas. So gravitational potential energy is the energy that you store when you are high up or when you are lifted up. If you lift something up into the air or put it on a high shelf, for example, it will gain gravitational potential energy and it will be stored. That gravitational potential energy that it stores there is converted into kinetic energy as that box falls. For example, I've just put this box on this waterfall. Here it's gained gravitational potential energy and is storing it. As it hits the water, really important for your exam because it comes up a lot, is the idea that gravitational potential energy, which I'll write as EP, is transferred into kinetic energy. Now, if we assume that there was no kind of friction and other forces playing into part here, then all of the gravitational potential energy that's up here would be transferred into kinetic energy. For example, if this box was storing 100 joules of kinetic energy, this would be all transferred to 100 joules of, sorry, I think I say kinetic up here. If this is storing 100 joules of gravitational potential energy, it would all be transferred to 100 joules of kinetic energy. And this is where you sometimes see those cheeky one marker questions again. And I'll explain how this happens in terms of this roller coaster. So just like the waterfall here, the roller coaster would transfer all the gravitational potential energy it has up here into its maximum kinetic energy when it's at the bottom. So let's have a look at this one question and we'll try and link these ideas together. It says point X on the roller coaster is 20 meters high. If the mass of the roller coaster carriage is 5,000 kilograms, so we've got a mass, calculate the gravitational potential energy of the roller coaster at point X. And we've also been given a gravitational field strength. So if we put these into the equation, we can do what we normally do. We can have a look and see that that's a height, that we've also got a mass, and we've got gravitational potential energy that we need to work out, and we've been given gravitational field strength. So we put these into our calculation where we've got gravitational potential energy from over here, from our data sheet, equals mass times gravity times height So gravitational potential energy equals 5,000 multiplied by 20 meters, just checking they're all in the right units before I put these numbers down, multiplied by 10. Now they will give you this gravitational field strength. It's quite an easy number to remember, 10 newtons per kilogram. They might be cheeky and give it to you as 9.81 newtons per kilogram, so don't be afraid if you see it like that, but normally it's rounded up to 10. So once you do this calculation, you'll see that the gravitational potential energy stored at this top of the roller coaster is equal to 1 million joules. And once you've done that massive calculation for 3 marks, I want to get you in the habit of looking how many marks the question is worth. You will sometimes notice, not always, but sometimes notice a 1 marker after it, saying calculate the maximum kinetic at a point at the bottom. And all you need to remember, just like when we were talking about these 1 markers before, they probably don't want you to do a lot of work for them. So the most times you just have to write down the same number again, 1 million joules. All of that potential energy is transferred into kinetic energy. So hopefully you've got that idea. Sorry about that. Hopefully you've got that idea. And here is one for you to try. Now, if you're doing the foundation paper, I'd like you to have a go at this question. And if you're doing the higher paper, I'd like you to have a go at this question. So have a go at those, look at the information, write it down, and then we'll come back and see if you got it correct. I'm just warning you that this one involves the most tricky rearrangement of the equation that you will have to do in the higher tier exam. So have a go at those. I'll check the comments while you're doing that, and then I'll come back. Okay, keep working out those questions. I'm going to help you just by highlighting the key bits, and then we'll go through and check that you got it right. So up here we've got a girl with a mass of 50 kilograms, jumps 2 meters high on a trampoline, calculate her maximum kinetic energy as she hits the trampoline, and we've got gravitational potential energy up here. Sorry, this shouldn't say gravitational potential energy, that's a mistake. If you're wondering why you got that wrong, that should say gravitational field strength. Okay, so apologies if you made that mistake. Gravitational field strength is 10 newtons per kilogram, and you should be able to work out that question now. Down below, we've got a book sits on top of the bookshelf. The gravitational potential energy of the book is 100 joules. The book falls to the ground with a mass of 200 grams, alarm bells, and calculate the speed of the book. So just one more minute, and then we'll go through and check, see if you got them right. Okay, what I'd like you to do is just quickly post your answer on Frog for me. So if you've got the comments all open there, if you did question 1 or 2, can you just post your answer on there, and we'll check to see if you've got them right. Okay, let's go through the first question then first of all. A girl with a mass of 50 kilograms, so we've been given a mass, jumps 2 meters high, calculate her maximum kinetic energy. Now, this is important. We've got some information like G up here, M and H, to calculate the potential energy. when she reaches that height, but we've been asked to work out the kinetic energy when she hits the trampoline, and that's the tricky bit to get our heads around. So if this is the potential energy, that's then all transferred into kinetic energy. So we can work out the potential energy by doing EP equals mass times gravity times height. And then we just put our numbers in. EP equals 50, check it's in kilograms, multiplied by 10, multiplied by 2, which gives us a gravitational potential energy of 1,000 joules. And then we have to look at the question and think, well, we've been asked to work out kinetic energy. And that's where your understanding comes in, that all of the gravitational potential energy is transferred into kinetic. So our kinetic energy answer is also 1,000 joules. Okay, so on the bottom here, we're talking about a slightly trickier rearrangement for the higher paper. So well done for those who've got their answers right. If not, just post it on Frog and I'll check to see if you've got them right. So a book sits on the top of the bookshelf. The gravitational potential energy of the book is 100. So we know that EP is 100 joules. The book falls to the ground and the book has a mass of 200 grams. So that's our alarm bells. We need to convert that mass into kilograms. So we divide by 1,000 and we get our mass of 0.2 kilograms. And we need to calculate speed. Now this is the trickiest rearrangement that you will need to do in the higher physics to calculate speed. So our general equation, I'll do it over here. Our general equation is EK equals 1/2 times m times v squared. But we need to rearrange it to make v equals, and hopefully you would have got that, is v equals the square root of kinetic energy divided by 1/2 times m. And then we can put our numbers in to calculate the speed at which they hit the ground. So if the book on top of the shelf stored 100 joules of potential energy, that would have all been transferred to kinetic energy when it hit the ground. So we know our EK is 100 joules. So to calculate our speed, we need to put our numbers in. So do it in a different colour. So V equals the square root of 100 joules divided by 1/2 times by our mass, which is 0.2. And if you did that calculation correct, you would have come up with a speed of 31.6 meters per second, remembering your units. And something like that would probably be around 4 marks, because you have to do a tricky rearranging of the equation, and you will also need to have the correct units. So very well done if you got that one correct. Okay, moving on then, I want to talk about forces, and I want to talk specifically about equal and opposite forces, because this idea is really common in the exam papers, and it explains how things move. So the idea of equal and opposite forces explains how things move, and they're often written in a question, which makes it a little bit tricky to understand in the exam, and it's one that people commonly get wrong. So I'll just introduce this idea here, is that when two objects interact with each other, they exert forces on each other that are, this is the important bit, equal in size and opposite in direction. For example, this person here sitting on the chair, he is going to exert a force downwards, and the chair is going to exert a force back on the person that is equal in size but opposite in direction. So it's the idea that all the forces come into pairs, and this is often the rule that we talk about when we're looking at reaction forces. So two objects coming into contact with each other and touching each other. So here we've got a man sat on a chair. He's exerting a force downwards of, say, 10 newtons, for example. Sorry, let's be more realistic, 100 newtons downwards, and the chair would exert a force which is equal in size and opposite in direction. That stops the man then falling through the bottom of the chair. But this does more. This explains how things move. And these are a couple of examples that you might see in the exam, which will throw you off a bit. This one says, the boat propeller pushed back on the water with a force of 20 newtons. So we've got a propeller pushing back with a force of 20 newtons. And the question is, why did the boat move forward? So for 2 marks, you'd need the idea of the water is pushing back on the boat. With a force that is equal in size and opposite in direction. So there's often 2 marks for getting those points in, that it's equal in size and opposite in direction. Similar idea then, I'm not going to write it again, but similar idea with when a man is jumping. So the idea that a man, when he's jumping, is pushing down on the ground with a force of 800 newtons. Why did the man jump upwards? And that same idea that if he's jumping down with a force of 800 newtons, then the ground is also pushing him up with a force that is equal in size and opposite in direction. So that force of the ground pushing him upwards will mean that the man will be able to jump. So just look out for these. If you're thinking about why is an object pushing backwards with a force yet it's going in the opposite direction, think about these pairs of forces that are acting together. So don't forget to continue to comment on the frog page if you have any more questions, and write your name so I know who is listening. A few more people have just joined us. So write your name on the frog page and ask any questions there that you have. Okay, moving on then, we're going to talk about resultant forces. So this next section is going to be about resultant forces. And you can think about the resultant force as the overall force acting on an object. Okay, that's how you can think about the resultant force. And that comes about because if you have an object, for example, I'll just draw a box. It's not a box. For example, if I just draw a box here, you have an object, you may have multiple forces acting on that object. For example, you may have a force in this direction and a force in the opposite direction. So when we've got several forces taking into play, it's important to know what the overall force acting on the object is. And it's important to think about which direction the force is acting in. So in this case, to the right, let's assume we have 50 newtons pulling the box to the right-hand side. And then to the left, let's assume that we have 40 newtons. With resultant forces, we need to take into account all the forces that are acting on an object. So if 50 newtons is acting in the right direction and 40 newtons is acting in the left direction, we have to take both of these into account. And to do that, if we assume that this is the plus direction and this is the minus direction, we would have plus 50 newtons, and we have to take away the 40 newtons so that we know overall that there is a resultant force of 10 newtons to the right. So for a resultant force question, you will probably be asked for 2 marks. So you'll have 1 mark for the working out what the overall force is and 1 mark for saying which direction that force is acting in. So it's easy just to give them one side a plus and one side of the minus, and then that will help you work out the overall force. I expect most of you will be able to do that just by looking at it, thinking, well, there's 50 pulling that way, 40 pulling that way. So overall, we've got 10 newtons pulling in the right direction. If we have a look at another example, we'll take a box again. but this time we'll have a look at several forces being into play. We'll have a look at 2 forces pulling in the right direction and 1 force pulling in the left direction. So on this side over here, let's assume that we have 30 newtons in this direction and 10 newtons also pulling in this direction. So this time we've got multiple forces acting to the right-hand side. Again, we'll give this the plus direction. And then we've got, let's assume on the left-hand side, 30 newtons pulling back. So again, we have to add up our forces on this side. So now we've got 2 forces. Overall, going to the right-hand side, we've got 40 newtons. And going on to the left-hand side, we've got 30 newtons. So our resultant force, our overall force, would be 10 newtons to the right. Or you can write 10 newtons to the right. Okay, so just have a look, think about what direction the forces are acting in, and remember to add up all of the forces that are acting on that object. So moving on with resultant forces then, this is the idea. There's a few rules that we need to remember. And that's it. In these resultant force questions, we need to think about the motion of the object, how it's moving. And the first thing we can look at is if it's stationary. So if an object is stationary, if the resultant force is 0, the object will remain stationary. Let's have a look at how a resultant force of 0 would come about. So it would come about if you had equal size forces acting in both directions. For example, if you had 5,000 newtons in the plus direction and 5,000 newtons in the minus direction, if you were to take the 5,000 newtons to the right and take away the 5,000 newtons to the left, you would end up with a resultant force of 0. And in that case, if the object is already stationary, it will remain stationary. However, if a stationary object experiences a resultant force that is not 0, it will accelerate. For example, if this car was parked, but then it experienced a resultant force in the right direction, because the force in this direction, let's give it a number, say 3,000 newtons, was greater than the force in the left direction, this would experience a resultant force of 2,000 newtons to the right. Okay, and because this was once stationary, as soon as it starts, it will accelerate. So it will go from 0 meters per second until whatever its final speed is. So that's what happens when it's stationary. Let's now look at what happens when the object is already moving. So when the object is moving, we can still think about it in terms of having a resultant force of 0. So let's have a look at that one first of all. If the resultant force is 0, the object will continue to move at the same speed. Now this is really important because most people get this wrong. Most people think that means it is stopped. It's not. If you have a resultant force of 0, you might have 5,000 newtons that way, 5,000 newtons that way. But if the car is already moving, it doesn't mean it's stopped. It means it's just traveling at a constant speed. It's not accelerating. On the other hand, if you've got a moving object which then experiences a resultant force, so one that is not 0, it will then accelerate. For example, if we had 6,000 newtons that way and only 3,000 newtons that way, the car would experience a resultant force of 3,000 newtons to the right, and therefore it would accelerate. So these two are both the same essentially. If it's stationary or if it's moving and it experiences a resultant force, it will accelerate. But the key thing that you need to remember is this difference. If the object is moving and the resultant force is 0 newtons, it will continue to move, but at a same speed or a constant speed. So here's a couple of questions for you to look at in relation to resultant force. They say, describe the motion of the following objects if the following forces were applied. So we're going to assume here that this parachutist is experiencing a downward force of 500 newtons and an upwards force of 500 newtons. Here it tells you the resultant force is 0, and here it says a boat moving to the right, and we will give that boat a forward force of 300 newtons and a backwards force of 100 newtons. So have a go at those questions. Think about if you can describe the motion of these three objects. So if you have a look at this first question, we'll go through the answers now. With the first object, you've got a falling parachute, so it's already moving. It's got 50 newtons in that direction, 500 newtons in that direction, 500 newtons in the other. So it has a resultant force of 0. So that means if we're describing the movement, this one here is moving at a constant speed. And in fact, another little link into your P2 is that we call a terminal velocity, when a falling object reaches a constant speed. For the second one, you've got a dog standing still, so he is already stationary. And he has a resultant force of 0, so his motion will just remain stationary. And finally, the boat moving to right, it has a resultant force of 200 newtons to the right, and that means the boat will accelerate to the right. Okay, so very well done if you got those correct. You need to remember that when they ask about motion, that's talking about the movement of the object and how it's moving, whether it's speeding up, slowing down, or staying the same. Okay, the final thing that I want to talk about today is distance time graphs, okay, and velocity time graphs. These kind of images that you'll see in your exam which confuse some people. Now, the important thing that I want you to do is whenever you get these distance time graphs or velocity time graphs is to highlight your axes to see what you've got. Have you got distance or have you got velocity? Because that's really important in your understanding. Because people make this far too complicated than they actually are. So we've got distance time graphs in this situation, and we've been asked to look at the motion between points A and B. So let's put the letters on there to help you: A, B, C, and D. The motion between points B and C, and then we've been asked between which points does the object travel the slowest, between A and B or C and D. If you have a think about those, and then we'll go over them. If you're higher tier, also think about how you would calculate the speed between points A and B. So just had a question about drawing distance time graphs. Yes, you might have to draw either a velocity or a distance time graph from some given data. Okay, so do be prepared to have to draw them as well. So let's check out this first point then. Here we've got something that says describe the motion between points A and B. So here's points A and B. And if you read the graph, what's happening? It's going up in distance as it's going up in time. So it must be moving. So the object here is moving because as time is increasing, the distance is increasing. And within all your cases you'll get for a distance time graph is that it's moving at a constant speed. So at a constant speed. And you can tell that by the fact that it's a straight line, okay? So we're just moving at a constant speed. Between points B and C, you need to read the graph carefully. Have a look. It doesn't change from 20 meters. So if you started at 0, you've gone to 20 meters, but then you stay there, at this point, you must be stationary. You must be stopped because you started your journey from 0, you've gone to 20 meters, and then you've stopped. And then at C, you continue your journey again. So for B, we're looking at a stationary object. And for C, it says between which points does the object travel the slowest? Well, we need to look at how steep the line is. So here, the line is steeper than C and D. So at this point, the object is traveling slower. And if you read the numbers, that'll make you remember that in the tests. Because if you look at them, this object here travels 20 meters in 40 seconds. Whereas between C and D, you only travel 10 meters or less than 10 meters in 80 seconds. So just do that double check to make sure you're getting it right. Final thing then for the higher tier, you need to be able to calculate the speed. And to do that, you need to calculate the gradient of the graph. And to do that, just draw a little triangle on your graph. It's been asked us between B and C. Sorry, between A and B. So we need to calculate the gradient of this line. So we need the difference in Y and the difference in X. So our difference in Y divided by our difference in X will give us the gradient and therefore the speed. So delta Y, if you look here, is 0 to 20, which is 20, divided by our difference in X, which is 40. So that will give us our speed or our gradient of the line. So if we do our 20 divided by 40, which is our gradient, we will get a speed of 0.5 meters per second. And if you remember the equation speed equals distance over time, that will help you remember because speed equals the distance divided by the time. Lastly then, we are going to look at velocity time graphs as our last thing in this tutorial. Now velocity time graphs, you need to look on the left hand side again, make sure you're talking about velocity in meters per second and time on the bottom. And if I put a couple of letters on here to help you, A, B, C, D and E. This question says describe the motion between points A and B, points C and D, and points D and E. If you have a go at those, and then these couple of things for the higher, if you're watching on the archive, you might want to pause and have a go at them. You've got calculate the acceleration and calculate the distance travelled. Now I'm going to go through them straight away now, but feel free if you're watching on archive to pause and come back. Just had a question about the speed equation. The speed equations, speed equals distance over time. Yes, you can use that to calculate the gradient. In fact, that's exactly what you're doing when you're calculating the gradient from the distance time graph that we just looked at. You were doing the distance divided by time. So that's what you were doing when you did your delta y divided by delta x. You were doing your distance divided by time. Now, unfortunately, this equation here, they don't give you on your exam data sheet. This is the one that they don't give you. They expect you to remember this equation, but that's exactly what you're doing as you are calculating the gradient. You're doing a distance divided by time to calculate that speed. Now we're going to look at something a little bit different here. If I just put these letters on again, we are going to be looking at a velocity time graph between points A, B, C, D and E. So we need to describe the motion between points A and B. And if you look at this time graph, you just need to read the axes to see what's happening. You start at 0 meters per second and you end up at 40 meters per second. So you must be speeding up. Now the science word for that is accelerating. But if you can't remember that, you can just simply say speeding up. Points C and D, let's have a look and read it off the time graph. At point C, you're at 80 meters per second, and at point D, you are still at 80 meters per second. So at this point, you are traveling at a constant speed. Lastly then, between points D and E, if we read it off the graph, you are starting at 80 meters per second and you are going down to 0 meters per second. So you must be slowing down or decelerating. Final couple of bits for higher then. You need to be able to calculate the acceleration between points B and C. So again, to do this, we need to calculate the gradient of the line, because if you think about it, acceleration is the difference in speed over time. So if we take the end point as V and the starting point as U, you could do it that way. You could take these numbers out and do 80, take away 40 over how many seconds? 10, 20, 30, 40. You could do it like that, or you're doing it by exactly the same way if you calculate the gradient. So if you go down like that, which I think is related to the kind of question that I got just a minute ago on frog, which is talking about can you just use the equation. If you find that way easier, then yes you can, but you're just doing the same thing. Difference in y divided by difference in x. So you're looking at 40 divided by 40, which will give you 1 meters per second squared. So remember that for the acceleration, the units, meters per second squared. Very final point then is for the velocity time graphs, you will have to calculate the distance travelled. And we're going to do that here for between the points D and E. So this was D and this was E, and we're going to look at distance travelled. To do that, you need to calculate the area under the graph. So you have a look at your points D and E, you draw all over your graph, and you draw the area that you want to calculate. So to calculate the area of the triangle, you need to remember to do the y value, multiply the x value, and then divide by 2. That's the bit that people forget the most. So in this case, we're going from 160 to 200, so this would be 40. And up the side, we've got from 0 to 80. So that's 80. So if we multiplied these two together now, 80 multiplied by 40, put it up here, 80 multiplied by 40, we would get ourselves the value of 3,200. Okay. However, that would give us the area of this whole rectangle. We don't want that. We don't want this bit. This is the only bit that we want. We just want the area under the graph. That's this bit here. I'll highlight that in red. This is the bit we want, the area under the graph. This bit we don't want. So you have to divide that value by 2, and that will give you 1,600 meters for the distance travelled between points D and E. So very well done if you got those correct. I'll stay online for a couple of minutes to answer any last questions. And if there's anything you're still stuck on, then feel free to come up and see us in the science department. So thanks very much for watching. I hope that was helpful for you. For those of you who've watched it on archive, I also hope that was helpful for you as well.